Hello and welcome. Today we're going to be solving the problem Mooclear Reactor. In this question, we are given n nodes, each with an unknown weight AI, and we are given m edges, where each edge has a known weight zi. And each edge represents a constraint. In particular, the sum of the weights of the nodes that it connects must be equal to the weight of the edge. So if it connects the nodes xi and yi, we know that the sum of ax and ay must be equal to zi. So we have to satisfy all of these constraints, and the question we want to answer is, given we satisfy all of these constraints, what is the maximum number of nodes that satisfy this inequality? So for each node, we're also given a value L and a value R, and we would like, if possible, for its weight to lie somewhere between L and R. So we're trying to maximize the number of nodes satisfying that inequality, given that we satisfy all of the edge constraints. And this is a tricky problem. It is going to involve several sort of quintessential silver algorithms. And to make progress on a question like this, we're going to want to start by analyzing several cases. And the recommendation that I'm going to give is we always want to start with analyzing a tree if we can. Then we're going to look at the problem on an even cycle, and then we're going to look at the problem on an odd cycle. And once we analyze these three cases, we should have enough information to fully flesh out our algorithm idea. So if possible, it's always a good idea to start with a tree because these are sort of the simplest that graphs can be. And here we have a tree on 4 nodes. We can see it has 3 edges. So for example, if we have the edge between A0 and A1 being 1, that gives us the constraint that A0 plus A1 must be equal to 1. So the sum of the first 2 nodes has to be equal to 1. We can see the constraint between nodes 1 and 2 is 7. So we get the equation that 1 and 2, the sum of those must be 7. And then finally, we can see that the edge weight between 1 and 3 is 0. So the sum of A1 and A3 must be 0. And the first thing that we have to realize is that when we have a tree, this system of equations that's produced has infinite solutions. And to prove that to you, what we can do is we can express every single node's weight in terms of the value A0. So the first node has value A0, and when I choose the value of the first node, that's going to fix the value of the second node. Then when I choose the value of that node, it'll fix the value of the nodes that it's connected to, and so on. This will propagate throughout the entire graph. So just choosing the value of the first node or the 0th node is going to determine the node weight for every other node in the graph. So what we get to do in a tree is we can choose this initial value. And in order to choose the best initial value, what we're going to do is we're going to take the intervals for all 4 nodes, and we're going to rewrite them so that they are in terms of A0. So we know that A0 has to be, or we really want A0 to be between L0 and R0, but we can also write constraints for L1 and R1, L2 and R2, and so on in terms of A0. So for example, if we know that A1 has to be between L1 and R1, but we know that A1 is equal to 1 minus A0, then this constraint is the same as A0 being between 1 minus R1 and 1 minus L1. So at any point in time in this problem, rather than having n different variables that we have to optimize over, what we can do is we can always convert all of the values into the perspective of the first node in our connected component. So we can just choose a random node in our connected component and then rewrite all of the constraints in terms of that first node. So if it's possible to satisfy the system of equations, we're just going to try to express everything in terms of the first node and then choose the best value for the first node so that we satisfy as many of these intervals as possible. And we can do that using a priority queue. We can do that using the sweep line algorithm. There's tons of different ways to determine sort of what is the maximum number of overlapping intervals in Silver. So once we reduce it to this problem, we just throw our favorite algorithm for finding the maximum overlap of a series of intervals, and we're done. But we have to be a little bit more careful when it comes to cycles because it may not always be possible to satisfy this system of equations. So here we have an example of an even cycle, and the analysis of the even cycle is very similar to the tree, except there's two cases. One case is that the system of equations has infinite solutions, just like we saw with the tree case. So I'm going to fix one of the nodes, the first node, arbitrary choice, and then once I fix that node, it's going to determine the value of every other node in the connected component. The other possibility, however, is that the system of equations has no solutions. And just to show you the math on this, if I have these four equations, then if I take their alternating sum, so what that means is I'm going to take the first equation, and then I'm going to subtract the second equation, then I'm going to add the third equation, then I'm going to subtract the fourth equation, and so on. What we're going to get is that the left-hand side here cancels out. For every copy of A0, I'm going to subtract a copy of A0. For every copy of A1, I'm going to subtract a copy of A1, and I get a 0 on the left-hand side. On the right-hand side, I get the alternating sum of the z's. So I get z0 minus z1 plus z2 minus z3. And what this tells me is that in order for there to be a solution to this system of equations, the alternating sum of the coefficients must, or the constants rather, must be 0. So for example, in the graph we have up here, if we can take the alternating sum, we'll see that there is a solution. So we get positive 7 minus 5, our current count is 2, plus 2 is our current count is 4, minus 4, our current count is 0. So as we go around the circle, we just take this alternating sum. We get 7 minus 5 plus 2 minus 4 checks out, becomes 0. So in this particular situation, we would be able to find a solution. However, if the alternating sum of the constants was not 0, then there wouldn't be a solution, and we would just return -1. So again, if our graph has an even cycle, we can analyze it the same way we analyze the tree, but we just have to make sure that the cycle ends up being satisfied in the sense that the alternating sum of its constants must come out to 0. The more interesting case is the odd cycle. And the odd cycle is interesting because one of two things happens. Either the system has one solution, or the system has no solutions. Again, we can write out sort of the system of equations here and take the alternating sum. But this time when we take the alternating sum, what we're going to end up with is on the left-hand side, we're going to end up with 2 copies of A0 and the alternating sum of the constants on the right-hand side. So we get Z0 minus Z1 plus Z2. And on the left-hand side, we get 2 copies of A0. So what that tells us is that this alternating sum of the constants must be even because we're told in the problem statement that A0 must be an integer. Not only does this value have to be even, if there are multiple odd cycles in the graph, this choice of A0 better align for all of the odd cycles because when we have an odd cycle, it actually fixes the value of A0. I don't get to make any choices when there's an odd cycle. So if there are multiple odd cycles, every odd cycle should imply the same choice for A0. If I end up with multiple odd cycles trying to set A0 to a different value, then that's going to be an impossibility case. So when I have an odd cycle, I actually have a nice benefit where I don't have to find the optimal solution because there's either one solution that is forced by the odd cycle or the system has no solutions and I can just print -1. So if my graph does have an odd cycle, I don't need to do sweep line. I don't need to do any priority queue nonsense. I just immediately know what every value in the graph is going to be. So again, we're focused here just analyzing one connected component at a time. In our code, what we're going to do is we're going to brute force over all nodes. When we find a new connected component, we're going to use DFS to search the entire connected component. We're going to record every cycle we see if it's satisfied. If it's ever not satisfied, we return -1. And then once we're done with that connected component, we fix all of the values of AI in that connected component, and we move on to the next connected component. So it's really sufficient to analyze just connected components on their own because, again, we can just brute force over each connected component independently. And if any of the connected components end up being impossible to satisfy, then the entire graph is impossible to satisfy. So with this analysis in mind, we're going to move on to the code. Note that the code for this question is quite long. However, if you've been studying Silver, a lot of the algorithm ideas are going to be familiar, right? So we've got initializing a graph, we're going to be performing DFS over the graph, and then finally we're going to be using some variant of a sweep line algorithm in order to find the maximum overlap of intervals. All of which are like very standard Silver techniques, but since we're just doing multiple of them in one problem, the code ends up being quite long. So let's take a look at the code. So what we've done so far is we've just read in all of the variables. So again, n is the number of nodes, m is the number of edges, L and R represent the intervals that we want each node weight to fall into. Adjacency stores our graph. And then we are also going to be creating 3 arrays that are currently unknown. So A is the edge of the node weights. We don't know what those are yet. We're going to be filling those in throughout the process. And then sign and constant are going to help us express every node weight in terms of the first node that we see in a connected component. So we can see that every node in the connected component can be written as the first node in the connected component plus some constant, or some constant minus the node weight of the first node in the connected component. So sign is going to store whether this value is positive or negative, and constant is going to store whatever this value is. It could be positive, could be negative, could be 0. And then we're ready to begin our search. So we're going to start by brute forcing over every node. And as we brute force over every node, we're going to be looking for a node that we haven't visited yet. And we're going to be using the sign value to figure out if we haven't visited it yet, or we could use A or any of these 3 arrays, or you could have a separate array for visited. But the point is, we're just checking, have we not seen node I before? And if we haven't seen node I before, then we're going to begin a depth first search on node I. You could equivalently use BFS if you wanted to instead. It doesn't matter so much. And the key idea is we're going to start filling in sign and constant. So we're going to try to write everything in terms of AI. This is the first node that we saw in the connected component. So we're going to express all of the other node weights in terms of AI. And we can see that AI can be expressed as 1 times AI plus 0. So sign is just 1 and the constant is 0. These values aren't too interesting, but all of the other values in sign and constant will be a little bit more complex. Then we're going to need to store some data. We're going to be storing the connected component itself. So what are the nodes in this connected component? And then we're going to have a stack to do DFS. You could do it recursively, but I'm wanting to avoid using a function here so I can break out of solution very easily, but that's just me being a little lazy. So I'm using a stack to do DFS. You could use a queue for BFS, whatever you want. There are a million ways to do this. And then while our stack's not empty, we are going to remove the top of the stack and we're going to visit all of the nodes that are connected to it. So we're going to loop over every node adjacent to X. And if we haven't visited Y before, then we can just update the sign and constant values for that node. So we know that A of Y is going to be equal to the negative sign of x times ai plus z minus constant x. Where did these values come from? They come from the fact that we know that a of y, or let's write it like this, a of y plus a of x is equal to z. And then if we rearrange this by subtracting a of x from both sides, we get a of y is equal to z minus a of x. And then we are rewriting a of x in terms of a of I. So my goal is to express all of the node weights in terms of a of I. So then I substitute in my current knowledge of a of x, which is just stored in sine x constant x, and I end up with a of y is equal to z minus sine of x times ai plus constant of x. And if you rearrange terms in this formula, you can see that we end up with this equation on line 33. So that allows us to solve for the sine of y. In particular, the sine of y is just going to be the opposite of whatever the sine of x is. And then the constant for y is going to be z minus the constant for x, which makes sense. It's going to be just whatever portion of the edge constraint wasn't satisfied by the current value for x. So we can update the values sine y, constant y, and then we're just going to add y to our stack and add y to our connected component. Not too interesting, just normal DFS where we're updating these two arrays along the way. What is interesting, however, is what happens if we find that we've already visited the node. If we've already visited the node, that means we have found a cycle. And in this cycle, we have to make sure that either, in the case of an even cycle, the sum of the constants is 0, or in the case of an odd cycle, we end up actually just determining the value of AI. So we're going to calculate sort of, are we in an even cycle or an odd cycle? So if we're in an even cycle, this value is going to be positive or negative 2. If we are in an even cycle, this value is going to be 0. And then B here is the sum of the constants along the cycle, or the alternating sum of the constants along the cycle. So for example, if I'm in an even cycle, so if the sum of my coefficients is 0, then I also need to require that the sum of the constants is 0. That's what we saw down here when we were saying that the sum of z0 minus z1 plus z2 minus z3 was equal to 0, right? So B stores that alternating sum of the coefficients. So if that's not equal to 0, then I'm going to need to return -1. I have an impossibility case. I can't satisfy this even cycle. There's a contradiction. So this is what we have to check for an even cycle. If there's an odd cycle, so notably that the coefficient of A0 ends up not being 0, it can be either 2 or -2, then we have to check first, is the sum of, or the alternating sum of the constants even? If it is, or rather, if it isn't, then we're in an impossibility case and we should return -1. If the sum is divisible by 2, then we're going to check, have I already assigned the value of AI? If I haven't already assigned the value of AI, then I can simply solve for the value of AI by dividing both sides by m. And then finally, what I want to do is I want to check is, if there was a value of AI already, is it different than what I now need to assign AI to? So if there was already a value stored in AI, but that's different than what I need to assign it to now, then that's going to be another impossibility case. The only way that this would occur is if there were multiple odd cycles in the connected component. So this would be, I found one odd cycle, that odd cycle said AI needed to be one thing, then somewhere later in my connected component, I found another odd cycle, that odd cycle disagreed with what AI needed to be, so then I get a contradiction and I return -1. So, but the point is, if I find an odd cycle, I'm going to know what AI is for certain. Then, finally, we're pretty much done, except for the fact if we didn't find an odd cycle. If we didn't find an odd cycle, then we need to choose the appropriate value of AI, right? So if we go back to the tree case here, right, there wasn't a value assigned to A0. Instead, what we would have to do is we'd have to look at all of these intervals and choose what is the best value of A0 so that it falls in as many intervals as possible. For now, I'm just going to say that we have a function called optimal A that solves that problem, and then we'll write optimal A later. But the point is we need to choose some optimal value for the initial node. Once we've done that, we just update every value of AJ in the connected component using the equations that we've already constructed in sine J and constant J. And then we're pretty much done. The last step is just count how many of the intervals ended up being satisfied. And for each interval that gets satisfied, we return one larger count. and then that gives us the optimal number of satisfied nodes. To find the optimal choice for A of I, we need to first start by expressing all of the intervals in terms of A of I. So we're just going to select the first node in the connected component, and then we're going to rewrite all of the intervals so that they are within the reference frame of AI. Once we've done that, we can sort the intervals by their first coordinate, and we can use a priority queue to loop over the intervals in sorted order and find what is the maximum number of overlapping intervals at any point in time. And then we're going to return a value for AI that exists within that maximum overlap. So what choice of AI will lead to as many overlapping intervals as possible? One thing that to note here is that there are two cases depending on whether the sign of AI is positive or negative for a given node. So for example, we can see that when we're calculating the value of A1, we can see that's equal to negative A0. So we end up subtracting R1 from the left and subtracting L1 from the right. If, on the other hand, the sign for A0 is positive, like in the A2 case, then the left-hand side, we just subtract the coefficient. So we end up subtracting 6 from both sides, and that is very easy to shift up and down. So there's going to be a little bit of casework here when we're sort of converting all the intervals over, but I recommend going through this math on your own. Probably just looking at the code here is not going to be super helpful. I recommend writing out all of the equations yourself and seeing in an example by hand how to construct these intervals. The math is on the screen, but you'll probably need to pause the video to work it all out. Then once I have everything in terms of A0, the last thing I need to do is apply sweep line or some priority queue idea to just maximize or choose the best value of A0. And the best value of A0 is just the value that lies in the most number of intervals. So we're just going to process the intervals in sorted order. And what this algorithm is doing, in case you haven't seen it before, is we are storing the number of intervals that are currently active. And every time we get to a new interval, we record the start point of that interval and we add its end point to the priority queue. If the minimum element in the priority queue is before my start point, that means that there's an interval in my priority queue that ended before my current interval has started. So what this is saying is that the one of the intervals in my priority queue does not overlap my current interval. So I'm just going to remove that value from my priority queue, and I'm going to keep doing that until all of the intervals in my priority queue overlap the current interval that I'm working with. So that way, after this while loop is finished running, the length of active stores the maximum, or just stores the number of overlapping intervals for this current interval. And after I have that value, I can check, is that number of overlapping intervals larger than any value I've seen in the past? If it is, I'll update maximum, and then I can set result to be start. So result is the optimal value of AI I'm choosing, and I'm just choosing AI to be the start of the interval that has the maximum number of overlaps. So I end up saying, okay, this is a really good choice for AI, but then if I ever find more overlapping intervals in the future, then result gets changed. And the thing that I return here is result, because if we scroll down to the bottom of our code, what we want in the end here is to assign a given choice to AI. So what value of AI will lead to a lot of intervals being satisfied? And that completes the code. So what you can see here, it's a pretty long code. We need one function in order to determine the best choice of AI when we don't have odd cycles. We need one function to perform this DFS search. Again, I chose not to put it in a function just so I could have these return values, but feel free to restructure the code. And then the rest is just simple things like reading input and printing your final output. So the core ideas here is we have one call to DFS or several calls depending on the number of connected components. And then we have this second function that uses either sweep line or some priority queue idea to find the maximum overlap. So two very standard Silver ideas just combined into one long code. So thank you guys so much for watching the video. I hope you had a good contest, and thank you. Bye bye.